So let's continue. On number 23, we are going to find the prime factorization of the number. The first step is to find any two numbers that divide into it. Okay, well, there's several, and you pick the one you find. So if you see 3 and 15, or you see 9 and 5, whichever ones you find are right. I'm going to use 9 and 5 because I have a feeling most of us will do that. 5 times 9 or 9 times 5 doesn't matter. When I look at the 5, it's done, isn't it? Remember, to be prime, you can only have factors of 1 in yourself. So 5 only factors into 1 in itself. So we're done with him. But the 9 still breaks down a little further. It breaks down into 3 times 3, doesn't it? Now 3 is a prime number also, 1 and 3. So now that we've got all of the ends of our branches down to prime numbers, we have the prime factorization of the number, which is 3, and how many of those did we have? 2 and 1, 5. A neat way to check is to multiply those back together again. 3 squared is 9 times 5 is 45. Let's do the 56. 56, I know, is 7 times 8. And again, any two numbers that you see, if you saw 2 and 28 and you want to go that route, you're sure welcome to. 7 is a prime number, so I'm going to go over to the 8. I know that 8 multiplies into 2 times 4. And now, although 2 is prime, 4 is not. So I'm going to break it down a little bit further into 2 times 2. Now, all of those factors are prime. So I'm going to circle the prime factors. I notice that 3 of them are 2s, so I can rewrite the prime factorization of 56 into 2 to the third power times that 7. Let's continue with 72. 72 is a product of 8 times 9. Or again, you can, any two numbers that you can show multiply to be 72 would work. So 3 and 24, or 6 times 12. You could just use any kind of different product that you see. I happen to know that 8 times 9 is 72. I can break 8 down a little further into 2 times 4. The 2 is prime, but this 4 isn't. So I'm going to break him down a little further. And as soon as the ends of those branches are prime, you stop. The 9 can be broken down now into 3 times 3. And again, once you get all of the ends of the branches to be prime, you're finished. And we can rewrite this guy as 2 to the third power times 3 squared. For the 140, that's 14 times 10. Remember when we were multiplying numbers by 10 and 100 and 1000? I can tell that this one is going to be 14 times 10. So I'm going to start there. But again, you can use any factors you want to, and we'll all end up with the same prime factorization. 14 can be broken down a little further into 2 times 7. Now, we've already seen these, so I know that these two are prime numbers. 10 can be broken down into 2 factors again, 2 times 5. Now, those are also prime factors. So the prime factorization of that number is 2 to the second power, 1 5, and 1 7. I like to put mine in order, smallest to largest. In fact, that's encouraged. Now, square roots. If A is a non-negative number, if A is a non-negative real number, the non-negative real number B, such that B squared equals A, is the principal square root. I'll show you another way to think about it, okay? If A of A and is denoted by B equals the square root of A. The inverse of squaring a number is finding the square root, okay? Some properties of square roots are that the square root of 0 is 0. That looks like this. The square root of 0 is 0. When we use the symbol, and it's called a radical, that's how we show a square root. The number underneath the radical is called the radicand. For example, the radicand in this term is 36. So the number underneath the radical is called the radicand. For any real number c, in other words, if you have to have a positive number, not 0, greater than or equal to 0 is what we're looking for. If the square root of c squared equals c, I said that all kinds of wrong. Let me stop. Let me show you. First of all, we're going to list perfect squares. A perfect square is this. So if I take the number 1 and square it, it is equal to 1. The number 2 and square it, it is 4. So here's what they're talking about. The base of 2 being squared is equal to 4. Because it is being squared, the square root of 4 is 2. Does that make sense? I'll show you another way to think about it. If I'm taking the square root of 4, the prime factorization of 4 is 2 times 2, right? For any 2 of something underneath, 1 comes out. But right now, we're not even getting into that, so let me back up. I just want to write all of the perfect squares that I can think of, up to 100. So the number 1, because it has factors of 1 and 1. The number 4, because it has factors of 2 and 2. 3 times 3 would be 9. 4 times 4 would be 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. And 10 times 10 is 100. So we're going to stop right there. Okay? Now, the base that was squared to get the 1 was a 1. The base that was squared to get the 4 is a 2. That's going to become important. Let's look at this guy. So we know that if they are perfect squares, when you take the square root, that's the inverse of it. So it's just giving us back the base. So what was the base that was being squared here? 9. And actually, I like to write it this way. If I know that 81 is 9 times 9, the square root says that for every 2 of something underneath, 1 comes out. So you can think about it that way as well. Now, let's go down here to number 31. We'll get back up to 29 in just a second. Okay, the square root of 9. Well, 9 is 3 times 3. So what was the base that was being squared? A 3. So the square root of 9 is 3 because it's giving us the opposite. What number was squared to make 9? Okay, what number squared gave us the 64? An 8. And the negative is after the fact. Up here, what number squared gave us a 1? A 1. And the negative is after the fact. Now, 29 and 33 I didn't do just yet for this reason. Remember, it's got to have 2 numbers that multiply out, 2 of the same number that multiply out to be a 64 or a 9 or an 81. With negative 1, the numbers 1 and 1 do not multiply out to be negative 1, so that didn't work. If I make one of them negative, now they multiply out to be negative 1, but they're not both the same number anymore. So this one is called non-real. In other words, it's not going to work. So 33. Think about that for a second. For the same reason, 7 times 7 make 49, right? That's not the negative 49 we need. If I make one of the signs negative, now they multiply to be negative 49, but in order for the square root to be possible, they have to be the same number. So this one is also non-real. And last one. So the opposite is true too. When you square a square root, the inside just drops down. We said that a square root and a square are inverses of each other. So if you have a square and you take the square root, the inside just comes out, right? So down here, when you squared a square root of the base, the inside is just, what's really happening, let me just say it this way, The square root and the square, because they are inverses of each other, they cancel each other out. So the 7 just comes down. Same thing here. That square root was squared. They're inverses of each other, so the inside just comes down. Same thing here. The square root and the square canceled each other out, so the 700 came down. But watch this. That square was also on this negative separately, but it's still on it. When you square that negative, it's like saying negative times negative, right? And that's going to give us a positive. All right, I'll see you in note 6.